Hey everybody, welcome to our next video all about chemical bonds. So I always thought that chemical bonds were relatively easy to learn because it's pretty self-explanatory. There's the three types of bonds and they do different things and that's what holds atoms together. And it all comes down to their electronegativity, how bad atoms want electrons. So what is a chemical bond? Let's just go ahead and define that first. Chemical bonds are an attraction between atoms that allows for the formation of chemical substances that contain two or more atoms. So we have our periodic table that has 118 elements currently. And we can take those 118 elements and combine them in a multitude of different ways via chemical bonds. And those chemical bonds are what allows for us to have the massive diversity with chemical compounds. We're combining these atoms together in order to make new substances, to make compounds. And of course, most of what we're familiar with are in fact chemical compounds, not just elements. So we're combining elements together to form more complex compounds by the way of chemical bonds. And of course, atoms want to bond together in order to lower their potential energy. They want to become more stable. They want to satisfy the octet rule. Atoms just bond because they're happier that way. They want to have a full outer shell of electrons that are similar to the noble gases, and that's what makes them really stable. And of course, depending on the types of elements that are attracted to one another, there are three types of chemical bonds that can occur. The first type of bond is an ionic bond. The second type is a covalent bond. And the third type of bond is a metallic bond. And let's just go ahead and briefly get into each of these. So an ionic bond is when you have a complete transfer of valence electrons from a metal to a non-metal. And when that happens, you're generating oppositely charged ions. So in this case, if we consider electron configuration, which we went over in the previous video or a couple of videos ago, this right here looks like it's going to be lithium, and that's because it has not only 3 protons in its nucleus, but it has 2 electrons in the first shell, and it has 1 electron in that outermost shell. This one right here looks like it's going to be fluorine. So I still have those 2 core electrons, but I have 1, 2, 3, 4, 5, 6, 7 valence electrons. So this is fluorine and this is lithium. Lithium is very unstable and fluorine is also very unstable. So in order for them to lower their potential energy, fluorine, which is the nonmetal, is going to rip an electron away from the metal. And that's because fluorine wants to gain 1 more electron to be just like neon. And that's exactly what it's going to do. Fluorine's ripping that electron away from lithium, because when lithium loses that 1 electron, 3 minus 1 gives me 2, it has the same electron configuration as helium, which is really what makes it stable. So atoms are bonding not only to lower their potential energy to become more stable, they want that full outer shell of electrons. So I have my metal, this electron is getting transferred from metal to nonmetal. So that's the key thing there, is ionic bonds always transfer their electrons, whereas covalent bonds always share their electrons. And that's because you have 2 nonmetals that are lowering their potential energy together. Because they have very similar electronegativities on the periodic table, they are going to share their electrons rather than the nonmetal completely ripping it from the metal. And of course, they could share their electrons in one of 2 ways. They can either share their electrons equally via a nonpolar covalent bond, or they could share their electrons unequally via a polar covalent bond. And a nonpolar covalent bond, a great example of that would be bromine bonded to bromine. So here's one bromine, here's another bromine. Notice the covalent bond, which is normally represented by a line in between them. That covalent bond is being shared equally. Those electrons within that covalent bond are being shared equally. Why? Because neither bromine is strong enough to either rip the electron away from the other, and it's also not strong enough to pull it more in one direction. Think of it as a tug of war where you have two guys that are equally jacked that are pulling for a tug of rope. Because they have the same strength, they're going to pull on the rope the same amount. It's the same way with elements. Because bromine has the same strength as another bromine atom, they're both pulling electrons equally across that bond. So this is a nonpolar covalent bond. As opposed to if I have a polar covalent bond, notice that your bond is still there. There's still a line representing them, which means that they're being shared. But bromine is a lot stronger than hydrogen. And your strongest element is fluorine, if you don't remember that. Your most electronegative element is fluorine on the periodic table. So bromine's pretty darn close to fluorine. Hydrogen's relatively far away. Because bromine is stronger or more electronegative than hydrogen is, it's not strong enough. Bromine is not strong enough to rip an electron away from hydrogen, but it is strong enough to just pull it more so towards itself. So they're still sharing their electrons, but bromine's kind of hoarding the electrons a little bit. And when that happens, bromine has a partial negative charge. So this little symbol right here is what we call a partial. It's not totally negative because it didn't steal an electron, but most of your electrons are going to live around bromine, whereas you're going to have a lack of electrons over towards your hydrogen. So they're still sharing, but it's an unequal sharing, and that is what we call a polar covalent bond. Happens between nonmetals, but with nonmetals that are relatively far away from one another on the periodic table. And your last type of bond is a metallic bond. And these, of course, happen between metals. So a metallic bond is a strong attraction between closely packed positive metal ions and a sea of delocalized electrons. So you have all of these positively charged metal ions that are next to one another. So let's say these are all copper atoms in this these little red spheres here. So these are all copper ions with a positive charge. And this lighter blue area is your electron cloud right there. So it's one massive cloud that surrounds all of those copper atoms. These dark blue spheres are your electrons, and these electrons are constantly moving in and around this whole entire structure, like so. Because they're constantly moving, those electrons don't belong to one atom, they belong to all of the atoms. And that's why metals have very unique properties. That's why they're malleable. That's why they're ductile. That's why they're great conductors of heat and electricity, because these electrons are constantly moving in between this network of positively charged ions. And we call that delocalization. So if you're delocalized, that means that you're moving around all of the time. If you're delocalized, maybe you went to school at Wallenpaupack and then you go to college in Florida and then you have an internship in California and then you decide to move over to Colorado. So you're moving all around, as opposed to if you're local, you kind of stay in one spot. And electrons in a metallic bond are delocalized. They're always moving. They don't belong to one atom. They belong to all of the atoms in a sea, is what we call it. And that's where we're going to stop with this video. This one was pretty short. But I just wanted you to get a refresher on the three different types of bonds because one of the units that we do go into does kind of reflect back on this information when we talk about the strengths of the different types of solids and all that. So if you have any questions, feel free to email me or to stop on by. Otherwise, I will see you in the next video. Bye.